Welcome to the deep dive. Today, we're looking at something potentially huge. It involves black holes and, well, a theory from Stephen Hawking that's been around for
And
decades.
Hawking radiation, yeah. It's a fascinating topic.
Absolutely. So our mission today is to really get into this, based on an article called "Has Hawking Radiation Just Been Detected?"
Mm.
I want to figure out what this could all mean.
Right. And the core idea, just to set the scene, is Hawking's prediction that black holes aren't completely black. They should leak radiation.
Leak. How does that even work? I thought nothing escapes a black hole.
Well, it's down to quantum mechanics near the edge, the event horizon. Think of empty space as constantly fizzing with pairs of virtual particles.
Okay, particle pairs popping in and out of existence.
Exactly. And right at the horizon, one particle might fall in while the other escapes.
And the escaping one carries away energy.
Precisely. A tiny, tiny bit of the black hole's mass energy. Over, incredibly long timescales, this could actually cause the black hole to evaporate completely.
Wow. Okay. But that radiation must be incredibly faint, right? Especially for the big ones we usually talk about.
Oh, absolutely minuscule for stellar mass or supermassive black holes. Their temperature is incredibly low.
So low it just gets lost.
Pretty much. Lost in the general background warmth of the universe, the cosmic microwave background. Utterly undetectable with current tech.
But, okay, this is where the article brings in something else. Primordial black holes.
Yes. These are hypothetical black holes, much, much smaller, maybe formed right after the Big Bang.
And smaller means hotter.
Exactly. Like a tiny ember glows hotter than a large cooling log. These primordial black holes would be significantly hotter and radiate much more intensely.
Okay, now I see the potential link. Detectable radiation.
Potentially, yes. And there's another twist.
Let me guess. Dark matter.
You got it. There's a theory that these tiny black holes could actually be some, or maybe even all, of the mysterious dark matter.
Right, the stuff we know is out there holding galaxies together, but we can't see.
Mm-hmm. So if they exist, and they're dark matter, and they evaporate, they should release energy we might be able to see, like a final burst.
Which brings us right to this new detection. An incredibly energetic neutrino spotted by the KM3 NET telescope.
Yes, the energy level is just staggering. Something like 100 to 200 peta-electron volts. Heavy.
And the article gives some context on that, doesn't it? It's, what, 10 times more energetic than the previous record holder?
Roughly, yeah. 10 times the previous neutrino record from IceCube, and something like 1,000 times the energy particles reach in the Large Hadron Collider.
Whoa. Okay, so that's really energetic. Could that be it? The last gasp of an evaporating primordial black hole.
That is the tantalizing possibility. Hawking's theory predicts that evaporating black holes should emit all sorts of particles, including neutrinos.
And because neutrinos barely interact with anything, they could travel across the universe to reach us.
Exactly. And a final violent evaporation burst from a very small black hole could theoretically produce neutrinos with exactly this kind of extreme energy. It fits the profile.
It's like, as the article puts it, hearing the black hole's last whisper.
It's a good analogy. A very, very loud whisper in energy terms, though.
So even though it's just one neutrino, its energy makes it stand out.
Immensely. Science needs repeatable results, more data points, but an event this extreme, this far outside the norm, you have to take it seriously.
The article compared it to, like, a single alien spaceship landing. One is enough to change the game.
It's that kind of potential significance, yes, because, crucially, our usual suspects for high-energy particles, things like supernovae or jets from supermassive black holes.
We struggle to explain this much energy in a single neutrino.
Currently, yes. Our models have a hard time pushing neutrino energies quite this high from those sources. It makes the Hawking radiation idea, well, quite compelling.
Okay, makes sense.
Yeah.
But hang on, if these things are exploding, shouldn't they be throwing off other stuff too, like light, photons?
That's the critical next step for verification.
Yes, absolutely. If it's Hawking radiation, you'd expect a corresponding burst of very high-energy photons, gamma rays, coming from the same direction around the same time.
So are people looking for that?
Oh, definitely. Telescopes are searching archival data, and they'll be watching that patch of sky. The challenge is that high-energy photons interact more easily on their way here.
So they might get scattered or absorbed, making them harder to spot than the neutrino.
Correct. Space is full of gas, dust, magnetic fields. Photons have a tougher journey, but finding that photon signal would be huge confirmation.
Okay, let's step back. If this pans out, if this neutrino is from an evaporating black hole and maybe they find the photons, What does that mean for physics? Big picture.
Oh, it would be monumental, truly. First, it's direct experimental proof of Hawking radiation, validating one of the most profound theoretical predictions of the 20th century.
Confirming Hawking's work after 50 years. Wow. Yeah. Second, it would be strong evidence that primordial black holes are real, and that they could make up at least some of the dark matter. That would be a massive step in cosmology.
Finally, a candidate for dark matter we can actually point to.
Potentially, yes. And third, it gives us a whole new way to study the universe at its most extreme, using neutrinos to probe quantum gravity.
Quantum gravity, the theory that marries Einstein's relativity with quantum mechanics.
The very same. The Holy Grail, really. Observing these events could give us experimental handles on physics that happens under conditions we just can't replicate on Earth. It opens a new window.
It really does sound revolutionary. Now, the article gave this a plausibility score, 6 out of 10.
Yeah, which I think is fair. It acknowledges the excitement, but also the caution needed.
Not proven, but definitely not ruled out. Plausible.
Exactly. It also rightly points out, astrophysics often throws curveballs, new phenomena, unexpected sources.
History is full of signals we thought were one thing, then turned out to be something else entirely.
Precisely. So we need more data, checks, maybe alternative explanations will emerge. But right now, for this energy level, Hawking radiation from a primordial black hole is a very strong contender.
Okay, so let's try and wrap this up. Key takeaways seem to be: this one super energetic neutrino could be the death cry of a tiny ancient black hole.
That's the essence of it, yes.
If confirmed, it validates Hawking's theory from the 70s. Big check mark for theoretical physics.
Huge.
It might tell us what some dark matter is made of these primordial black holes.
A major piece of the cosmic puzzle potentially falling into place.
And it opens up neutrino astronomy as a tool to probe really fundamental physics, maybe even quantum gravity.
A whole new observational frontier.
It really does feel like, science fiction territory becoming actual science.
It often does, doesn't it? The universe is stranger and more wonderful than we usually imagine.
So maybe a final thought to leave people with. If one tiny neutrino can carry this echo of a black hole's end across the universe, what else is out there? What other subtle messages are flying past us, just waiting for us to build the right ears or eyes to detect them?
That's the exciting part, isn't it? The constant potential for discovery.
Indeed. Well, thanks for joining us for this deep dive today.
My pleasure.